Okay, let's run through two more properties of the Poisson process, the time homogeneity property and the Martingale property. So the first one concerns this transition probability from time s, where we've counted k events, over to time t, where we've counted n of them. And we saw that this calculation resulted in a probability that has the same distribution as the increment. In other words, the increment just has to count the n minus k events that are left over. And if you write out the distribution of it, it's Poisson, not surprisingly, but importantly, it doesn't depend on s and t individually. This is what the time homogeneity property is all about. It means that the transition probability depends only on the length of the time that is given to us, not necessarily where that interval starts. So the length of the interval is t minus s. That's what this distribution is dependent on, and it doesn't depend on s and t individually. So you could have actually started at any time. You could have started at time 5 or time 100 or anything else. As long as you have adjusted the length of the interval accordingly, you will get the same transition probability. Here is this probability adjusted, where we're going to start at time 0. That's my choice for the starting time. And then in that case, the interval ends at time t minus s, right? From 0 to t minus s is the same length of time as from s over to t. And you write out this distribution, and then not surprisingly, you get the same exact thing, meaning the right-hand side here is the same one as we got here. There is one more kind of caveat to this, and another special property of the Poisson process is that you could even start counting at 0. And, in other words, in this part of the formula, I'm assuming the usual condition, which is n0 starts at 0. And then all I have to do is count up the remaining n minus k events. So this formula also holds, although it's not strictly part of the time homogeneity per se. This is the only thing needed for time homogeneity. So, I'm essentially equating these two, and that's my condition for time homogeneity in general. And then the Poisson process will have this extra bit. So here's the description. For any time s and h, I'm going to start the Poisson process at time s in some state, and I'm going to evolve at h more time units where it has some other state n, and that probability is the same one as moving from time 0 to time h. And in fact, for any s, this would hold, right? So the probability doesn't depend on the starting point. Only the length of time that has elapsed, in this case h, matters. And then there's an additional kind of feature for the Poisson process, so this should be crossed out. It doesn't need to be here. Is that the number of events counted in this length of time h is just the difference of where we started to where we ended. But the time homogeneity itself is really this particular property here. So let's look at the Martingale property. From the picture below me, you kind of get the sense that the Poisson process is not going to be a Martingale, because Martingales stay level over time. They don't increase like the Poisson process does. So what we'll do is we'll just subtract off the mean. The mean of the Poisson process at time t is mu t. That's the expected number of events in t units of time. So let's try m being a Martingale and see if we can verify that. That means verifying two conditions. One is the expected value of the absolute value is finite, and then the best prediction of the future state should be the current value. So those are the two things to verify. The first one is simple. This is the triangle inequality in the first part. The difference is smaller than the sum of the absolute values. This is deterministic, so no expectation needed. Both are actually positive, so we can drop the absolute values, giving me 2 mu t, and that's clearly finite, and that's check on the first one. For the second one, we're going to apply the Markov property first to get me a conditioning on m at time s. The next thing is the recognition that knowing n at time s implies we know m at time s, and so we can just simply condition on the Poisson process itself. Simpler, take out the deterministic part in the next step, and now I'm getting ready to apply independence of increments, which is why I'm adding and subtracting ns here. This is what's known, so this is taking out what's known. That's a property of the conditional expectation. And the next thing is applying the independence of increments property. I'm conditioning on an increment, namely ns minus n0, which is independent of the increment nt minus ns. And the conditioning therefore is irrelevant, therefore it can be dropped, and therefore all I have left is this increment, the expected value of the increment here. And next, what we see is that the expected value of the increment becomes mu times t minus s, and there's a little bit of a mess up here. This needs to still be t, right? And then the mu t cancels, and leaving, so this is wrong again, this is mu times s, right? So I messed that up. So this t stayed, right? In other words, this t remained intact. I don't know why this got replaced by the mu s here. This is still the mu t, and it cancels out with this mu t, leaving ns minus ms. So this is a little bit wrong, leaving m at time s, which verifies the Martingale property. So I'll fix that in the final version of the slide. Okay, so I'm not going to run through the other martingales that are available. Here is just a list. We saw this first one. There is a martingale related to the second, the process squared. That's this one right here. There's also the exponential martingale, similar to what we saw for the Brownian motion. And then a quick note regarding optional stopping, which we've seen many examples of for the Brownian motion setting. Same thing follows here. For martingales, you can take m at some random time, hitting time, stopping time, and its expected value under some conditions will be equal to the expected starting point. And we can try this out, for example, with the kth jump time, where we know the process will have that many events. So if tk is the time at which we count the kth event, then n at time tk is equal to k. So this simplifies the application of optional stopping in all these examples, because you see that as we plug in nk here, the randomness part will kind of vanish, and so you'll get a number of results this way. So the first martingale here will get you this result right here. So simply plugging in tk for t here and taking the expectation and applying optional stopping will get you that the expected kth jump time is k over mu. Similarly, you can use this martingale here to get the variance of this jump time. And then lastly, you can even get the moment generating function. So this is the moment generating function of the kth jump, and that's something you get by applying optional stopping to this this martingale. So if you want to practice these on your own, you're welcome to, but that's the end of this lecture.